Welcome to our discussion today of calculating the energy of phase changes. In our last lecture, we talked about on the molecular level why the energy of phase changes in heating, water, ice, and steam were different. Today we're going to apply numbers to those and use them to do some calculations. Let's get started. So the first one we're going to talk about is specific heat. So the specific heat of a substance tells you how much energy is required to heat 1 gram of the substance up by 1 degree Celsius. So the specific heat units are going to be something like kilojoules, the energy required, per gram degree Celsius, per 1 gram and 1 degree Celsius. So they're more complex units we've used in the past. We'll work with them today. And in the last lecture, you learned that steam is easier to heat than ice or water. You learned why from a molecular perspective that would be the case. And so today we're going to learn how to use the numbers. And here are the numbers. So steam, you can see, has a value of 1.99. It has a very low specific heat, or at least a low one. Ice is 2.11 in the middle-ish, and then water is 4.18, substantially higher than both. Now, what this specific heat means is for water, say for example the 4.18, that tells you it takes 4.18 kilojoules to heat up 1 gram, so 1 little gram of water, 1 degree Celsius. So basically a gram of water, because the density of water is 1 gram per cubic centimeter, and a cubic centimeter is equal to a milliliter, it takes about 4.18 kilojoules of energy to heat up 1 little milliliter of water by 1 degree Celsius. Of course, if you wanted to heat it by 2 degrees Celsius, you would require twice the energy of this, so you'd have 8.36 kilojoules to heat up 1 gram of water by 2 degrees Celsius. And vice versa, if you wanted to heat up 2 grams of water by 1 degree Celsius, you'd need twice the energy. All right. So let's do some calculations involving these numbers. So the question is, how much energy would it take to heat up 5 grams of water from 22 degrees Celsius to 30 degrees Celsius? So we know we have 5 grams instead of 1 gram, and we know that number. So we know that for water, it's 4.18. Whoa, that's just totally wrong. For water, it is 4.18 kilojoules per gram degree Celsius. Now, we don't have 1 gram or 1 degree Celsius. We have 5 grams. So to get the 5 grams to go 1 degree Celsius, we need 5 times this energy. So I'm going to simply multiply this by 5.00 grams. Now notice here with my units, this gram and this gram will cancel. And when I do 5 times 4.18, I end up with 20.90. So I get 20.90 kilojoules per degree Celsius. So this is the energy it takes to heat up 5.00 grams of water 1 degree Celsius. But we don't want to heat it by 1 degree Celsius. We want to heat all the way from 22 to 32, and this is a 10 degrees Celsius, 10.0 actually, degrees Celsius change. So I'm going to need not just this energy, this is the energy it takes to go 1 degree Celsius, I'm going to need 10 times that. So to find the final answer, I'm going to take 20.90 kilojoules per degree Celsius and multiply by my temperature change here, which is 10 degrees Celsius. Notice here the degrees Celsius here and degrees Celsius cancel, and that means I'm going to need 209.0 kilojoules of energy to heat 5.00 grams of water from 22 to 32 degrees Celsius. Awesome. So basically notice, because I had more than 1 gram, I multiplied by the grams I had. And because I'm going more than 1 degree Celsius, I multiplied by the degree Celsius. And that gave me this large amount of energy that I need to just heat up 5 grams of water 10 degrees. All right. So this comprehension check, I want you to go ahead and try these two questions on your own. Hit pause when you're ready to continue on. You think you have your answers. Hit go and we'll look at the answers. All right, here we go. Let's get started. So how much energy would it take to 32.6 gram sample of water from 18.5 to 75.6? Well, I'm going to know right away, I need to figure out what a temperature change this is, how much of a temperature change that is. So to do that, I just take, of course, 75.6 and I subtract from it 18.5. I find that's 57.1 degrees. So I need to heat it up by 57.1 degrees Celsius. Now I know that I have a specific heat for water of 4.18 kilojoules of energy per 1 gram of water and per 1 degree Celsius. So to do this, I say, okay, I don't have 1 gram, I have more than 1 gram. So I'm going to multiply the 4.18 by 32.6 grams. And that's going to take care of my grams here. And then I'm like, oh, and that would be the amount of energy it takes to go 1 degree Celsius, but I have to go 57 times that. So I would then multiply by 57.1 degrees Celsius for how much temperature change there is. That would take care of my degrees Celsius, and I'm just left with kilojoules. So I just do equals. When I multiply those together, I'm going to need 7,780 kilojoules of energy to raise 32.6 grams of water from 18 to 75. So that's a lot of energy. All right. So next we have to take a look at this other problem. We have 56.2 grams of water at 35 degrees Celsius, and we add 224 kilojoules of heat. Now, up here it took 7,000 kilojoules to raise 32 grams of water by 57 degrees. And here we only have 224. So we should be expecting a relatively small temperature change because not only do we have a lot less energy than 7,000, we have more water than we had up here. So it's going to be harder to heat up a bigger sample. It's going to take more energy. So to do this, here's the first way of approaching. There's several ways to approach this. There's no correct way as long as you get to the right answer. I'm going to say I have 56.2. I know that water has this number, specific heat of 4.18 kilojoules per gram degree Celsius. I'm going to multiply that by my 56.2 grams. And what that number is going to tell me, so my grams cancel. And what I get from that is I get 2,349. And I'm going to keep all my units for right now, well, all my digits. And that's the kilojoules. Notice I have kilojoules per degree Celsius. Per degree Celsius. So this number is the energy required. So the energy required to heat by 1 degree Celsius. So to heat this 56.2 grams by 1 degree Celsius, I need 2,300 kilojoules. The problem is I only have 224. I don't even have enough to do 1 degree of Celsius. So the next thing I'm going to do when I do this, I'm going to actually divide this number into my total energy. And that will give me the proportion of a degree, the less than a degree that I need. So check out how this works. So you have 224 kilojoules of total energy divided by 2,349.16 kilojoules per degree Celsius. Now, this is a little sloppy here, I apologize. When you do that, you end up with so the kilojoules cancel, leaving just degrees Celsius. You end up with 0.095 degree Celsius. I did it again. That should be a 5. Now, when you add that to your 35, of course, you get 35.095 degrees Celsius as your final temperature, barely warmer than the 35. Now, that's one way of doing it. If that dividing makes sense to you, you divide, your total by what you need for 1 degree. Or you can set up like a stoichiometry problem with unit analysis. So if I start here with my number, so I know I have 224 kilojoules, over 1. And I'm using this as my conversion, kilojoules per degree Celsius. I'm going to set up so that kilojoules are on bottom. Kilojoules are on top, on bottom here. So I'm going to put the 2,349.16 kilojoules per 1 degree Celsius up here. Notice my kilojoules cancel, top and bottom. I take 224 divided by this, and I get that same 0.095 degrees Celsius from that. And then I add it, and of course I get right back to that answer as I should. So 2 methods of doing it, whichever makes the most sense to you. Awesome. Go on to the next slide now. Now enthalpy changes. So we need to learn how to work with those enthalpy changes. So the enthalpy heat, right? Remember, enthalpy is a fancy pants word for heat. So the enthalpy of fusion tells you how much energy it takes to melt 1 mole of the substance. Notice here, before specific heat talked about per gram per degree Celsius. This one is just per mole. And there's no degree Celsius because during melting, the temperature doesn't change. So for example, the enthalpy of fusion of water is 6.01 kilojoules per mole. What this means is it takes 6.01 kilojoules to melt 1 mole of water. Now here, this thing here is going to be a little bit funky for us. We're going to need to convert our grams into moles before we can use these numbers, these enthalpy numbers, because they're quoted in moles instead of grams. Just how it's done. Now the enthalpy, the heat of vaporization, tells you how much energy is required to boil 1 mole of the substance. For example, the enthalpy of vaporization of water is 40.7 kilojoules per mole. This means that to boil 1 mole of water, you've got to put in 40.7 kilojoules once you get to 100 degrees Celsius. Not in order to get there, but once you get to 100 degrees Celsius, you heat the water up. At that point, you still have to add 40.7 kilojoules just to get that water to boil, that whole mole of water to boil. Awesome. Let's do some practice. I'm going to the next slide. So let's do these 2 problems together. We're going to calculate how much energy is required to melt 63 grams of water, and then how much is required to boil 63 grams of water. Now in both these cases, when we're talking about the energy required to melt, we're assuming it's already at 0 degrees Celsius ice. And here for water, to boil the water, we're assuming it's 100 degrees Celsius water, and we're just doing the melting and boiling points. All right. So the first thing to do, of course, we know that water has this enthalpy of fusion of 6.01 kilojoules per mole. Now what that means is we need to convert these grams into moles. So over here I'm going to start with that. So I'm going to say 63.0 grams, and I'm going to convert that to moles. When I look up on the periodic table and add up the molar mass of water, I find that it is 18.0 grams for 1 mole, and that's H2O, H2O. So what I end up with is 63 divided by 18, and that gives me an answer of 3.5 moles of H2O. Now I know that for every 1 mole, I need 6.01 kilojoules. So if I have more than 1 mole, I'm going to need more than that. So all I'm going to do here is take my 3.5 moles of H2O, and I'm going to use unit analysis this time. And I'm going to say, hey, I want moles on bottom. So my 1 mole goes on bottom, and my 6.01 kilojoules go on top. And notice here moles cancel. And I end up with 6.01 kilojoules times 3.5, which gives me an answer of about 21.0. And this should really be 3.50, I apologize. 21.0 kilojoules of energy required to melt it. Awesome. Now another way of approaching this is to start like I did before and say, hey, I know it takes 6.01 kilojoules per mole, and then just to multiply that by the 3.50 moles, moles would cancel, and you'd end up with the answer of 21 point equals that guy down there. So two ways to approach it, whichever makes the most sense to you. Yeah, whichever makes the most sense, totally fine, totally appropriate approaches either way. So now we're going to do the same thing, but we're going to try and boil that 63 grams of water. Now, of course, I need to convert these grams into moles, which we've already done up here. So I know that this is equal to 3.50 moles of H2O. And now I'm just going to use these two methods real quick. So I'm going to do the first unit analysis one. I'm going to say 3.50 moles of H2O. And I know the heat of vaporization, or the enthalpy of vaporization of water, is 40.7 kilojoules per mole. I'm going to write that over here actually. 40.7 kilojoules per mole. So with unit analysis, I have moles up top, so I want moles on bottom. And then I'm going to have the kilojoules on top. And of course, the 40.7 goes on top with the kilojoules, and the 1 goes on bottom. Moles cancel. I have 3.5 times 40.7, and that gives me an answer of 142 kilojoules. Now I can do it that other way as well. I can say, hey, I want to start with this number because that's what makes the most sense for me. I know I need 40.7 kilojoules for every mole. And I'd say, okay, so if that's for 1 mole, then I just multiply by 3.5 moles to get the answer. And that gives me that same 142 moles, or kilojoules I should say, and the moles cancel. So two equivalent methods. Awesome. Now let's put it all together. We're going to calculate the energy required to heat 45.0 grams of ice from negative 100 degrees all the way up to 200 degrees Celsius. So we're going to go through two phase changes. We're going to heat ice. We're going to melt that ice. We're going to heat the water. We're going to boil that water. We're going to heat that steam. So we're going to put all 5 of those steps together. To do that, I'm going to do the work on this phase diagram so we can kind of see it. So we're going to say that this is negative 100. This is the 0 degrees Celsius, where water melts at. Up here is, of course, 100 degrees Celsius. And up here, let's just call this negative or 200 degrees Celsius. Now, it's not quite to scale. Notice that this 100 degrees is the same size as this 100 degrees, but we're going to make it work. So now down here, the numbers we need is for this part when we're heating ice, we need to know the specific heat of ice, which is 1.99 joules per gram degree Celsius. And across here, we need to know that number for the heat of, or the enthalpy of fusion, which for water is 6.01 kilojoules per mole. And then through this part, we're going to be heating water. So we need to know the number for water, which is 4.18 joules per gram degree Celsius. And across here is the heat of vaporization, and that's going to end up being for water 40.7 kilojoules per mole. And then this part is steam, and we need the number for steam, which is 2.1. Oh, I have those backwards. This one should be the 1.99. I apologize. Joules per gram degree Celsius. And this one down here should be the, oops, messed up again, 2.11. All right. So down here, what we're going to do is we know it takes 2.11 joules per gram degree Celsius times, we have how many grams in our problem? Oh, I didn't write that down. Let me skip back a step. 45 grams. Let me write that up here. 45.0 grams. So we have 2.1 joules per gram degree Celsius, but we have 45 grams. So we have to multiply by 45.0 grams because we have more than that. And then instead of just 1 degree Celsius, we want to go from negative 100 to 0, this part where it's ice, so times 100 degrees Celsius, because that's our temperature change. We're going to heat up by that much. And that's going to give us a value. We take 2.11 times 45 times 100. And that gives us a value of 9,495 joules. Now notice these other two units here are in kilojoules, so 1,000 joules. So to convert this one to kilojoules, we need to divide by 1,000. So this is equal to 9.495 kilojoules. And we made that switch because we're going to need kilojoules to compare all the energy at the end. All right. Now our next thing, we need to convert this 45 grams into moles because these are kilojoules per mole. So I'm going to do that right here, 45.0 grams over 1. And I'm going to convert that using the 18.01 or 18.0 grams over 1 mole. And we find that that number, 45 divided by 18, is 2.5 moles. 2.50 moles. So the energy in this range is just the 2.5 moles times 6.01 kilojoules per mole. So I'll write that down, 2.50 moles times, moles go on bottom, 1 mole. To melt 1 mole requires 6.01 kilojoules, and that's going to equal 6.01, 15.0 kilojoules. So it took 9 kilojoules to go from negative 100 to 0 to heat all that temperature range, and then 15 kilojoules to just melt it. So it's way harder to melt than it is to heat up by 100 degrees, which is kind of crazy. All right, the next one is this one. So we need to figure this one out. So again, I'm going to say, hey, I know it takes 4.18 joules per gram degree Celsius, but I don't have just 1 gram. I have 45 grams. So I'm going to multiply that number by 45 grams. And I'm not going up just 1 degree Celsius. I'm going from 0 all the way up to 100 from when I'm heating water. So times 100 degrees Celsius. And what I get from that is 4.18 times 45 times 100, 18,810. 18,810 joules. Now again, because these guys are in kilojoules, I'm going to switch them all to kilojoules. So that is equal to 18.81 kilojoules for heating the water from 0 degrees Celsius up to 100 degrees Celsius. Now notice that took a little bit more energy to do that, all that heating of the water, than it did to melt the water in the first place. And notice also that it's about twice as much energy as it is to heat the ice the same temperature, and that's because this is about twice of that one. All right, so now we've heated our water. We've put in 9.4, about 9.5 kilojoules to heat our water, to heat our ice up to 0 degrees, another 15 kilojoules to melt it, another 18 kilojoules to heat it up to 100 degrees, and now we have to boil it. So we have to do this part. And again here, just like the fusion, we're going to do 2.50 moles, and we're going to use this number like a conversion factor. So we're going to put 1 mole on bottom, and we're going to put 40.7 kilojoules on top. Moles cancel. And when we take 2.5 times 40.7, we end up with 101.7. So about 102 kilojoules. Wow, that took a lot of energy to do that. I mean, this was 18 kilojoules to heat from 0 all the way to 100, and then 100 kilojoules to boil it. So that's quite a bit. And then over here, we do one more thing. So from 0 to 100, just like before, we take the 1.99 joules per gram degree Celsius. Now that's for 1 gram, but we have 45 grams. We multiply by 45.0 grams, and we multiply by 100 degrees Celsius, because we're going from 100 degrees Celsius to 200, so we're heating it by that much. And we take 1.99 times 45 times 100, we end up with this 8,955. 8,955 joules, because the degrees Celsius and the grams canceled. Now I'm going to switch that to kilojoules and say that's 8.955 kilojoules. And now I'm ready to start adding all these up to see what the total energy is. So I take this one, so I'm going to say, so this is the total energy is equal to the energy to heat it up, heat the ice up, 9.4, let's call that 9.5 kilojoules, and plus 15.0 kilojoules, the energy required to melt that ice, plus the energy required to heat the water from 0 to 100 degrees is 18.8, plus over here the energy required to boil that water, 102 kilojoules, plus the energy required to take that steam from 100 to 200 degrees is about 9.0. When we add those together, we take 9.5 plus 15 plus 18.8 plus 102 plus 9, we get 154 kilojoules. Awesome. That's the energy it would take, 154 kilojoules, to take 45 grams of ice from negative 100 all the way up to 200 degrees Celsius. Whew, that was a lot of work. Glad you stuck with me. Give a shot today's in-class work.